Welcome back, folks. This is the second installment of intermolecular forces and how intermolecular forces affect properties of macroscopic properties like solubility and solids and melting points and boiling points, etc. So recap of day one, molecules are attracted to other molecules in general, and those forces are called intermolecular forces. Collectively, they're also called van der Waals forces. Often in this particular presentation and in other presentations or discussions of these types of forces, intermolecular forces will be abbreviated as IMF. Two major categories of intermolecular forces are the dipole-dipole attractions and dispersion of forces. Dipole-dipoles are being demonstrated, by the way, by this picture in the upper right corner, where you have two molecules of hydrogen chloride that are attracted to each other. So the positive dipole is being created around hydrogen and the negative dipole around the chlorine, and from one molecule to another molecule. So the number of molecules necessary for intermolecular attraction, minimum of two, and they have to be attracted to each other. And by the way, anything that's inside a molecule is often referred to as an intramolecular force rather than an intermolecular force. So an intramolecular force would be covalent bonds, ionic bonds, metallic bonds, etc. While intermolecular forces are between two separate molecules. Dipole-dipole attractions, again, positive dipole from one molecule to negative dipole of another, and hydrogen bonding being the strongest type of dipole-dipole attraction. Dispersion forces are where you have a non-polar molecule and there's a temporary shift of electrons in one molecule to one side that then causes another atom or molecule next to it to have its electron shift as well, creating temporary dipoles. So you have a polarized atom, a temporarily polarized atom that causes a polarizability in another atom, and that shift or attraction is then keeping those two substances together because of that attraction. Another general list, once again, I mentioned this when I presented this originally, that this list is in order of strength, but bear in mind that the numbers are not absolutes. So for example, there are going to be ion-induced, let me give you an example here, grab my pen. So when you have a hydrogen bond, for example, not all hydrogen bonds are stronger than dipole-dipole attractions. You'll notice that the range of dipole attractions go from 5 to 25 in their energy strength, while the hydrogen bond goes from 10 to 40. So while in general, hydrogen bonds are stronger than dipole-dipole attractions, there are some dipole-dipole attractions that would be stronger than hydrogen bonds. Same thing, by the way, with dispersion attractions. Dispersion attractions can be stronger than hydrogen bonds if the polarizability of the non-polar molecule is strong enough to do it. But in a general trend, the hydrogen bonds are stronger than dipole-dipoles, which are generally stronger than dispersion forces. It's a general trend. So whenever you're looking at an exam question or a problem, you should be looking at other data to be able to support that rather than just making general claims or accusations. That said, again, hydrogen bonds are generally stronger than dipole-dipoles. Dipole-dipoles are generally stronger than London dispersion forces. And in this particular data table, there's also the combination where you have an ion dipole, where you're combining, let's say, an ionic compound with a polar molecule. You have ion-induced dipoles, where you're putting ionic compounds into non-polar molecules. And then there's also dipole-induced dipole. So an entire list of these combinations and mixtures. So what properties are due to intermolecular forces? The greater the strength of the intermolecular force, that will have an effect on melting point, boiling point, vapor pressure, evaporation, and surface tension. By the way, a number of people do try to make a correlation or a causation between density and intermolecular force. To let you know, there is no good direct causation. There's going to be some correlation, but basically people try to make that connection and it is not there. So the ones that we want to focus on are the melting point, boiling point, vapor pressure, surface tension and evaporation, there is no real good connection between that and density. So let's start taking a look. So in general, the larger the intermolecular force, the higher the boiling point, the lower the vapor pressure, the higher the melting point, and the stronger the surface tension. Now, granted, for those astute people who are looking at this, you will notice that there's definitely going to be a correlation between the strong surface tension and the low vapor pressure, which also has a correlation to the high boiling point. So the surface tension is the ability for the molecules to attract to themselves on the surface and form a tight skin across the top of the surface. And if that is a very tight skin, there's not going to be a whole lot of molecules coming off of the substance, which means you'll have a low vapor pressure. And if you have a low vapor pressure, then it's going to take a lot of energy to make that substance boil. Okay? And as we go through this, hopefully that will become more clear. So here are some examples of essay questions that you might see to have you explain on an exam, for example. So, for example, can you explain why the noble gases have that trend in their boiling point? And then you should also be able to make a trend of looking at the alkanes. So you'll notice you have CH4 going all the way to C10H22. What is the relationship in the boiling point, or for that matter, the melting point of those substances? How would you explain that trend? Give you a moment to do that. So the noble gas trends, the larger the atoms, they have more space for electrons to shift. This allows the electrons to be more polarizable. That is a term, and that is a term that oftentimes graders like to see. The term polarizable means you understand that the electrons have the ability to shift and get moved within the atom or molecule. In this particular case, it would be atoms, since we're talking about the noble gases. This causes a stronger dispersion force, so the boiling point is higher. So again, just to summarize, noble gases, the larger and the more massive and generally there's a relationship to mass, but it's better to say the larger volume of the atom. The larger volume of the atom allows the electrons to shift more within it, causing it to be more polarizable. The more polarizable the atom, the higher the boiling point will be. In the hydrocarbon trend, the more carbon atoms, the larger the molecule. The larger the molecule allows for a stronger dispersion attraction, which would cause the higher boiling points. So generally, the same explanation is being used for the hydrocarbon trend, except that we're now talking about short molecules versus long molecules. The shorter molecules are less likely to be polarized, while the longer molecules are going to be easier to polarize. So let's take a look at same formula, but different boiling points, and if you can come up with an explanation as to why. So here are pentane, 3 isomers of pentane. Pentane is C5H12. One of the structures is just the straight chain of pentane, which you can notice is the first structure here, and it has a boiling point of 36 degrees Celsius. Methyl butane, which has a branch coming off of it, which looks like this, has a boiling point of only 27.9. And then the 2,2-dimethyl propane is this structure, the very last one at the bottom. And it has a boiling point of 9.5 degrees Celsius. So you'll notice that there's a decrease in the boiling point as you change the structure. Looking at the structure, or looking at what is drawn to the left, the first structure at the top is pentane, and it goes down in order. Can you explain, using those structures, why those boiling points get consistently lower? No, the different molecular surface area. Again, we're talking about the ability to polarize those electrons. All of the molecules have the same mass, but the straighter a molecule allows for greater polarizability of the electrons, or basically more surface area allows those electrons to shift and move, creating a stronger dispersion attraction. Other conceptual essay questions that you should be able to answer. Why does salt water have a higher boiling point than pure water? What happens to boiling point as the concentration of salt increases? That's a third essay question. What happens to the melting point of ice when salt is added? Oftentimes people want to use an intermolecular force attraction for this, which would be a great thing to try to do because it would make sense. However, it does actually go down more due to entropy, which we will talk about in our thermodynamics unit. So the two questions I'd like you to try right now is, why does salt have a higher boiling point than pure water? And what happens to the boiling point of water as the concentration of salt increases? Give you a moment. So salt water has a higher boiling point since the ion-water attraction is going to be stronger than the water-to-water attraction. Another way of describing that is the ion dipole attractions in the saltwater solution are stronger than the hydrogen bonding attractions in pure water. And as we take a look at water boiling, as more water evaporates, the concentration of the salt water would increase. If the concentration of the salt water increases, there will be more dipole, ion dipole attractions, which are stronger than the dipole-dipole attractions, which would cause the boiling point of the water to increase. So when you do add a little bit of salt to water in pasta, some people think that that is designed to increase the boiling point, which it does, but the amount of salt that you're adding is going to only increase at a very small amount. Granted, as more water evaporates, the boiling point will increase slightly as you're doing it. So here is an overall flowchart summary of all intermolecular attractions. Hopefully this will be helpful for you to try and piece all this together in a visual sense. Intermolecular forces, again, IMFs, are collectively called van der Waals forces. So all of these together are called van der Waals forces. Mixtures with ions versus polar molecules versus non-polar molecules. Mixtures with ions will have ion dipole attractions. Polar molecules will either be, will all be dipole-dipole, which some of them might be the hydrogen bonds that we've spent some time talking about. And non-polar molecules are dispersion forces, which those dispersion forces are also called Lundgren dispersion forces. The generic trend, the general trend, is described at the bottom of that page, where the weakest are the dispersion, going to the strongest, which are the ion dipole. And again, there are going to be some exceptions to that. Again, you'll have to look at data in the questions that you were provided to make sure that you are using all the information you're given. But hopefully this diagram would be helpful. I'll give you a moment so you can copy this down. Also, some people like to have a flowchart of how to try to figure out which type of intermolecular force is available. This version is this picture is a good picture of it. Let's see if I can give you a little bit more view. The first question is, are there ions present? If there are ions present, you're going to be shifting over to the right side of this particular diagram. And the ionic bonding examples versus ion dipole examples if there are no polar molecules present. If there are polar molecules present, or if there's only, then you'll have the ion dipole attractions instead. If you're back at the top, are ions present? And you answer no, then you answer, are there any polar molecules present? If the answer is no, then you just have dispersion attractions. If there are polar molecules present, hydrogen bonds, are there hydrogen atoms attached to N or F atoms? If the answer is yes, then you are going to have hydrogen bonding. If not, you'll just have dipole-dipole. Bear in mind, I do want to review with you that all of these substances in here will also all have dispersion attractions, because once again, everything has a dispersion attraction possibility. The dispersion forces only occur when it's in non-polar molecules. Give you a moment to copy that down. So this is the end of part 2. In part 3, we'll talk about other attractions other than intermolecular forces. So you hopefully this will give you a good summary currently of how intermolecular forces are attracted to each other and what properties are caused by intermolecular forces.